Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects. Welcome to Thermal Lens, a special series focusing on thermal remote sensing, created by me, your host Rachana Mamidi, Agnieszka Sojinska, and Jennifer Susan Adams. Agnieszka is currently a research associate at the University of Leicester in the UK and has been working in the area of thermal remote sensing since 2017. Jennifer is a postdoctoral researcher at the University of Zurich in Switzerland and is currently focusing on measuring land surface temperature over forests. Agnieszka and Jennifer are also chairpersons of the Thermal Remote Sensing Special Interest Group of EARCEL, the European Association of Remote Sensing Laboratories. This group aims to bring together all the relevant stakeholders and provides a communication platform in the form of workshops, special sessions, seminars, and more. In today's episode, Agnieszka and I chat with Charlie Siggs, a commercial agronomist at constellr, which is a German satellite company specializing in thermal intelligence. Charlie has a background in agriculture and has been solving problems in the agriculture industry for over 15 years. In this episode, we will learn how agronomists use satellite technology to monitor and predict plant health. From commercial considerations to the essential skill sets, we explore the multifaceted world of agronomy and satellite applications. So welcome to the podcast, Charlie.
Thank you. Nice to meet you.
Before we dive in, Charlie, what is an agronomist doing in a satellite company?
That's a very good question. I started out as an agronomist, about 16, 17 years ago now. And it was about in 2015 that I started to get involved with satellite imagery. And I was working for a company called Syngenta. And for them, we were using the technology for assessing fields. It enabled us to do it scalably through there and to see the health throughout the season and giving us extra data onto crop performance to help us with managing varieties, understanding how they performed to help us in promoting them and also position them correctly with farmers. And following that, I did a lot of work within Eastern Europe with those tools and how we could develop them. And then I moved into the digital agriculture department, moved over to the US and North Carolina for a couple of years and did some really exciting projects over there, working with drones and also satellite data from there. And for me, it's been a real eye-opener to see how we can scalably monitor crops now. For agronomists, a lot of the old ways have been through going out and walking those fields, and satellite imagery really gave the ability to monitor it remotely and then highlight those fields that you need to go and see first and make an action on with the farmer, and also to help us get a better understanding of different fields across in different regions. So I spent since 2015, so 9 years now, working in that space. And then I was approached by constellr 18 months ago. And it was really exciting because it was a technology that's really, I think, revolutionizing agriculture and what we have in remote sensing.
So you just mentioned constellr, and basically your experience was before mainly in the traditional way that is visible, right? Well,
Yeah.
now constellr's area is thermal remote sensing. So can you tell us how can we see any of the plant stress in thermal remote sensing?
Yeah, so with thermal remote sensing, it's enabling us to see the crop temperature. And what that's indicating is the level of stress and the water availability to the plant. Because when the plant has sufficient water, that's transpiring up through the plant and evaporating and keeping it cool from there. And when the plant doesn't have sufficient water and it's too hot and there's a very high rate of evapotranspiration happening, then we see a rise in that temperature occurring. And we also get indications in terms of what the water holding capacity of the soil is based on the different plant temperatures that we're seeing. And by being able to observe that temperature, we can see the symptoms days, sometimes weeks before you'd be able to visibly see a plant start to wilt.
All right. So basically, we have plant stress due to water that we can see up front. And is that also visible in the visible wavelengths?
Not in the visible ones, no. So with those, we can only really see the changes in the visible color, which is too late in terms of taking an action that can have an impact and stopped it affecting the yield so much. So when the crop starts going from most of the crops being a green color and then they start to go more yellow, lighter green when they have less water, it's often too late for us to take an action. And that's where thermal really enables us to take that action earlier on the crop.
Oh, interesting. Is the water stress that you talk about observed the same way for agricultural crops, the same way as for, let's say, trees in a forest or other green spaces?
Yes, so with all plants, you will be seeing the same response in terms of temperature and the water availability as well. I have a main focus myself in agriculture, but we also look at forests as well. And with them, we see that, yeah, there is that difference in the temperature. And it can be a very good indication for areas that are potentially at risk of fires within those forests. If there's not sufficient water there, then they will become drier and more. There's more chance of those trees catching fire. And a very interesting area, which I've been learning about myself, is with urban heat islands. And you see a big variation, particularly where you have a lot of green spaces. It's much cooler there compared to the actual buildings and other artificial structures that you have in place.
That's interesting. You mentioned so many other applications, but before we, go into that direction, what kind of spatial resolution do we need to observe water stress in agriculture?
Yeah, so for agriculture, we ideally need at least below 50 meters or so. And this is due to field sizes. And in the big growing regions, the field sizes, you're looking at an area of 10 hectares average size for them. And you want to be able to see the differences between fields because there is variation due to cropping when they plant it, the different variations of soil types across a field, and you need to be able to detect that stress. So below 50 meters provides us with that sufficient resolution to do that. If you go down much lower, there are potential applications for a precision application where they want to do it on maybe a row or a tree by tree or a plant by plant basis. But in terms of the uptake of that technology, it's actually still quite low and it's quite expensive to implement at that level. So it's what level do we need to help farmers transition from what they currently have to a level that's sufficient for their current level precision of application for them. So within the 50 meters, in order to see the less than 50 meters, so that variation within a field, and also to enable scalability across a number of ranges. For the small holders where they've got fields of less than a hectare or less than an acre, it's going to be not providing them with the data that they require to make so much on the field level. But what we find is in those areas is that their current level of precision is very low, and it's an improvement on what they currently have, especially when it comes to temperature and stress observations within a region.
And since you mentioned precision, how precise are we talking about, and what kind of accuracy is usually needed for these kind of observations?
Yeah, with the precision, a lot of farming equipment, particularly in big areas, if we're talking about the Midwest of the United States, Brazil, Eastern Europe, some parts of Asia, Australia, those ones, the equipment width can be 36 meters, and that's for a sprayer, as an example. And so, if you have a data that's within that range, it's helping to them to adjust the application rate. And they do something called variable rate application, which is across a field, you have differences in plant growth and its nutrient uptake, or maybe there's disease or insect pressure, and they will apply a product on there at different rates across in different zones within there. And that's quite often limited now by the width of the machinery and also the speed in which they can adjust it. And blocks of 30 meters, 30 by 30 meters, are sufficient for those larger scale farms in their application. We're seeing a lot more now with the advancement of robotics, that in some areas it's starting to become a lot more precise and they're starting to go down to the plant level. Greenhouse agriculture, they're able to do that now because they can implement sensors and cameras within the greenhouse. We can't do that in the outdoor field ones, but they are in certain crops which aren't grown over such large areas, such as vegetables, which tend to be in smaller fields and more concentrated regions. They will be starting to go down to within 5 by 5 meter in terms of their precision. And eventually they want to go down to the plant level, but that's depending on how fast the robotics advance to be able to do that, and also what the pricing is for those for people to implement.
Yeah, how expensive the plant is, and yeah, of course.
Mm-hmm.
And what about radiometric accuracy or temperature accuracy?
So the temperature accuracy needs to be within 2 degrees on there. And reason being for that, if we take a crop such as maize, it starts to experience heat stress between 30 and 35 degrees Celsius. And if your temperature accuracy is, say, 5 degrees range from there, there can be a big difference. Say if the temperature is at, if it's over 30 Celsius, but then you're getting a reading of 27, that can have a big impact on what you're interpreting in terms of stress. The same goes for cold. Maize is around below 10 degrees Celsius. It starts to undergo cold stress. And so you need to have that accuracy range within there to ensure that you ensure you're getting the right readings to know if it's going under stress or not. And it's particularly critical for predictive modeling in agriculture now. The modeling is used for yield prediction, also the growth and development of the plant, predicting when it will hit critical stages. And for those, they really need accurate data to ensure they get accurate prediction of yield.
And we're talking now surface temperature and not air temperature. Is that right?
Yes, talking with surface temperature in this case as well. And in terms of with air temperature, that is used a lot. But what we've seen recently, and we just done a analysis looking at land surface temperature compared to where the weather stations are located, and you can have tens of kilometers between weather stations, and a weather station may be reading 30 degrees, but then we can see within that distance to the other weather station, we saw a land surface temperature range of 30 to 50 degrees Celsius within there.
Yes, this is a common misunderstanding when people think that air temperature is the same as surface temperature. Well, surface temperature can be much higher, so we can have 25 degrees on air temperature, but we can have 35 already on the surface. So this is actually practically very crucial for the plant stress, I imagine.
Yes, it is indeed.
Yeah, I think we also talked about it quite in depth, this difference between air and land surface temperature in the first episode, Agnieszka, of the special series of the thermal lens.
Yes, that is correct. The episode with Mike Perry. So you mentioned already thermal, but as far as I know, constellr also has sensors in visible wavelengths. So why do you need both, or what particular wavelengths do you need to analyze plant stress?
With the visible, it also helping us to identify areas of cropland within those by looking at that visible length. And we can also use the visible and the near infrared from there to look at the overall crop health. land surface temperature gives us indications of what the temperature is of the canopy and water stress from in there. And by taking the visible and the near infrared and that normalized difference vegetation index that I mentioned, NDVI, we can look at the overall crop health within there. And that's useful for other applications, as I said, about variable rate. It's commonly used for fertilizer applications such as nitrogen fertilizer. And by combining, you need a combination of not just thermal, you need the other areas in there to give you that interpretation of what the overall crop health and stress levels are as well. And that's why we require those visible and near infrared ones too. And also giving us an indication, chlorophyll content and what the photosynthetic activity will be within the plants. And they need to be combined if we wanted to be able to identify diseases or within them, or maybe a insect pressure that's occurring or another. Then you need to have different data sources in order to accurately identify them, which is one of the reasons. And also by having the visible, we're able to, in some cases at requests, downscale the resolution of our thermal data to actually see variability. In some cases, a customer may not want to they may find that the accuracy of temperature isn't critical for their application. They want to see what the variability is across a field. And so they would want to go down to a lower resolution. So by downscaling and providing that at say 10 by 10 meters, we can fulfill the need of that customer in that specific case.
So would you use, in this case, only satellite imagery, or is there any data fusion with aerial or in situ sensors?
We will use, in some cases, we're working with customers and clients going on a collaborative journey where we're exploring, and some of them have sensors in place. And the sensors we can fuse with our data because there's also need to have that high temporal frequency on an hourly basis in some cases. And by our data improves the spatial coverage of those sensors, and the sensors can improve the temporal coverage that we can provide. And that's going to be critical in order to deliver the data that's needed for accurate observations, such as in cotton, which is a high value crop, where there's a lot of conversations going on about how they can improve water efficiency. A lot of the textile companies want to be able to monitor how much water is being used on a cotton crop. We need to have in-field sensors which are providing that hourly frequency of data, and then combining it with our data to improve the spatial resolution that they have there, and so that there's fewer sensors within it as well. And another case is that thermal data, the land surface, could be used to identify fields and regions of the field where there's a stress event occurring. And an agronomist or a farmer could go out there, they could fly a drone and then take that drone stitched image, which would be the visible and near infrared, and get pinpoint down to several centimeters of which plants and which exact area there are issues. And in some cases, just using that image, they could identify what disease it is or if it's a weed in that region of the field.
Charlie, you mentioned identifying or detecting diseases in crops. Is it also possible to predict any diseases in crops?
Yes, it is. And that's one of the key things about having both the visible and the thermal within there. And a lot of disease prediction, temperature is one of the key inputs and variables within there. And one of the others is precipitation. And so using those, and you also need historic data about the area, and also to capture data on disease spore movement too. But the the temperature is a critical input into the majority of models out there, which rely on that precipitation and also solar radiation within them. So we have several clients that are looking in how they can use it to improve disease forecasting. Example would be for Asian soybean rust in Brazil, which can cause billions of dollars worth of damage each year and reduction in yield. And any way that they can improve that is beneficial, and our data can be added into those models to help them have more accurate forecasts.
That's very interesting. So, to create all these models for detection or forecasting, what is the optimal time of the day to observe plant stress?
Yep. So the optimal time would be from around 12 p.m. to 2 p.m. in the day when you have the sun at its highest. So there's going to be the highest level of photosynthesis occurring, and also when there's most likely we're going to observe heat stress in that period of the day.
And this holds true across all latitudes.
Yes, majority of them. And in terms of you can also so the main period is between say your 10 a.m. to 2 p.m. within those period, and the majority is going to be around the in the 12 p.m. to 2 p.m. in the afternoon.
And how many observations typically are required per day or per crop season for both forecasting as well as detection and other modeling as well?
Yeah, so the observation it varies according to the cropping and also what the objective is that they have to do. And there's particular times during the season, planting time and germination, and when the crop emerges, particularly crucial because that's with if you don't have a good emergence, then that's going to have a big impact on the yield. So there needs to be regular monitoring, ideally daily, from those to understand okay what's happening from the crop. And then another key period example would be during pollination. And during this period needs to be understood what is happening to the crop, particularly in terms of the temperature, because if you have too high a temperature, then that affects the pollen, and you don't get as good pollination, which has the one of the biggest impacts on yield. And also, we have during critical stages of growth and development of the crop. In some regions, they have to apply several fungicides onto a crop. Potatoes, an example, in the Netherlands, they're applying 14 or more fungicides in one season. And they need to know okay, what the growth and development is of that crop and have regular observations happening for it too. Whereas a crop such as winter wheat, which is planted in October time, during the winter, you don't really need much observation because it isn't really growing. But then when the temperature starts to increase and it really starts to grow, normally around March in most of the northern hemisphere, that's when you would need to increase. So in some cases, you would need, in some crops, you need it during at an hourly basis during the season because there's such rapid phases of growth and development. And then sometimes you'll need it for every day, and then some crops maybe like once a week. So there's a large amount of variation within there, and the critical periods tend to be during the spring and summer months in the northern hemisphere, both northern and southern hemispheres.
Well, this is quite a lot of inside information. I was wondering, do you only use temperature as an input, or are there any other products that you create or derive? Evapotranspiration is one product quite well known in the thermal remote sensing community. Do you use that or any other products as well?
Yes, so we also use evapotranspiration, and that's used by clients for calculating the irrigation requirements of a crop. And as I was saying, in terms of a lot of them been using air temperature, but we talked about the difficulties in spatial resolution with those. And what we're enabling is to understand the evapotranspiration rate across a field so that irrigation can be adjusted for the different areas within the field. And the evapotranspiration also gives an indication of how much water is available to the crop. If it's got a high rate of ET, then it has sufficient water available to it. And we recently collected some images, and it was very clear to see helping identify which fields are irrigated, particularly if you've in a hot area. This was in Brazil. The irrigated fields were considerably lower, and there's a higher rate of evapotranspiration occurring on them. And it can also be used in the predictive models that I mentioned earlier.
This is very interesting, yeah. So, how about we zoom out a little bit? So, we've had already a little bit of a talk here on thermal lens about different sensors and different opportunities. And now there are three sensors built by national agencies that are coming. That is LSTM from ESA, SPG from NASA, and the Indian-French collaboration creating the mission, which is actually supposed to start the earliest of those three, that is Trishna. And so if those missions are promising basically a daily revisit altogether because they want to collaborate. So if we have those missions in a couple of years' time, why do we need commercial companies at all?
That's a very good question. And we need companies such as Constellr in terms of that you said a couple of years before those missions become available. And we will be providing data that helps us to start to understand LST. And LST, particularly in the agricultural space, we're very early on in the research and development side of this technology compared to particularly the visible spectrum of light. And a lot of customers that we're speaking to, they're only just starting to test and evaluate it. And we can provide that data to them for them to start learning about thermal data, how it can be applied, and how it can best be used. And so when those public missions come available in the data, it's a much smoother transition. And also, we need to have historic data available in order to solve the challenges that we face, because we're seeing increasing numbers of droughts, heat waves, flooding, and which is putting a severe amount of pressure on agriculture. And in order to combat those, we need to have data as soon as possible to understand what practices are coping with stress the best, such as regenerative agriculture. It's enabling there to be more water available to the plant and helping it to cope with stress conditions much better than conventional plough practices, as example. And we need to start accumulating data on that to understand, okay, which are the best methods to help us combat the challenges of tomorrow. And that's one of the key things, is just having that data early.
And then when these missions appear, are you going to use the data from these missions too? Is there going to be a data fusion approach?
Yes, so our focus currently is on providing that LST data, and we do already fuse and harmonize the data that's currently available, and we will incorporate that with our missions that we'll be launching, and also from the public missions as well, because we need as much data as possible to really get that better understanding.
Okay, interesting. So there's a lot of information that is being generated by Constellr towards modeling or towards forecasting or detection or prediction. But at the end of the day, who exactly is looking for this kind of information? Is it the local governments because they want to gain further insights into granting farmer subsidies, or is it farm unions, or is it individual farmers? Who is really interested in this information?
It's a broad range of stakeholders across the agricultural industry. Yes, governments are one of the key potential clients of ours. They are using it for understanding what the cropping is across the country, what the stress levels are, and for them, yield forecasting is critical to understand in some countries for food security to know how much they're going to have of the staple crops such as wheat, maize, and also what they're going to have to distribute in terms of insurance out to those farmers and helping them to map it out. In India, for example, they subsidize the insurance there, and in some cases farmers aren't getting payouts because of the weather station to them is 10 kilometers away and not actually measuring on their field where they've actually had stress and had a poor yield for them. And the government organizations also have their own research and advice that they provide to farmers, and they want to incorporate it into those. We see that a lot in Africa and Asia. The governments there want to be able to provide advice, particularly for their agronomists that are out on the ground visiting farmers, helping them to be more efficient as well with them. And also, some areas they want where they're particularly scarce on water, they want to be able to monitor how much water is being used on different farms for them.
Yeah, so I was actually curious now that you mentioned India and also crop farm subsidies and crop insurances. Usually in countries like India or a lot of African countries or Latin American countries, the farm sizes are much smaller than compared to, let's say, Western Europe or in the US or other parts of the world. So how does this change the modeling or the techniques employed by constellr or in general thermal imaging techniques?
Yeah, so with the insurance and you're saying with those smaller farms, it's a case of that they are using models based on weather stations, which can be very sparsely distributed in an area. And also, it may be that it's difficult to maintain those weather stations as well. And there may be gaps in the data potentially if there's low level of connectivity in the region that they're operating. And what our data can help is in terms of actually better understanding of what the temperature and crop stress is between those weather stations for them to provide more accurate calculations and then what the insurance payouts are within those different regions. And this is critical because there's a real issue generally across agriculture across the world, and farmers are struggling financially. And there needs to be accurate ways of making sure that they're getting the insurance claims that are representative of their farm, not of a region that's several kilometers away from them.
Right, we have a huge bias in terms of distribution of the air station. They're mainly focused in Europe and North America, but all the other world, which is also obviously producing lots and lots of food, they need those stations. And we have also this issue in terms of validation.
I always wonder how scalable are these applications across geographies, because different geographies come with very different challenges. The local politics are different, the local governance is different. For example, we were talking about small farm sizes. In India, farm sizes are like half an acre sometimes or a quarter acre because they're passed down generations, and then at every generation they get split into n number of parts. So it's always very curious to me the kind of applications we develop, the satellite applications we develop in one part of the world, how scalable they are. So, how scalable are thermal applications, for instance?
They're highly scalable across in different regions just because it's really providing us with temperature variations across large areas for them. And there are limitations, like with all satellite remote imagery, in terms of if there's a high amount of cloud, then unfortunately we can't collect data on that day. And so the areas where there's most likely before until we have sufficient data to do more modeling. Where there's less cloud, we'll be able to collect more data and provide more observations for those ones. But as we collect more data, then we're able to potentially model in terms of what the temperature is when there's cloud, such as diurnal temperature cycle modeling. We can start to do that and then prove that, particularly across cloud covered areas.
To these different stakeholders within a particular geography or across geographies, what exactly are you providing? What kind of insights are you providing? Is it satellite imagery or information? So essentially, in what form are you providing the information and the insights?
Yeah, so we're providing data to those customers, and we provide it as land surface temperature, and that centers files directly to the customers. And going back to the other customers that we have, we are also working with manufacturers of inputs, so people that provide agrochemicals such as fungicides and herbicides, and fertilizer suppliers as well. And for those companies, what they want to do is to be able to advise farmers on when the best time to apply their products is and how much as well. And also for demonstration of what they can do. They have their own software departments where they've been using remote sensing for a number of years already. And what we do is provide them with the LST data as a TIFF file, and then they put that into their systems and they use it to analyze the fields that they're looking at. And they do an analysis to look at what the stress was occurring across there. There may be some examples where they use it to compare different products, how they perform in drought conditions, or they can use it for yield prediction models. We've worked with people that they've done it there to look at as an input to help improve those yield prediction models that they have. The reason why they have those is to help advise the farmers on how much input to use. If they've got potentially a very high yield, then they can afford to spend more on inputs, and they want to protect that yield as well. So it's more crucial for them to do. Whereas if it's lower, then there's less of an incline to apply them. And they're also the companies providing seeds and those varieties, and they provide advice based on the climatic conditions of the farm and the farmer's fields. They have algorithms that run an analysis of that, and then look at which, based on their trial sites that they have, which products perform the best in similar climatic conditions, and then recommend those. And the data we provide can be used to help improve the analysis of those climatic conditions for them. And what I mentioned earlier was growth stage prediction of the plant, and fungicides and these other products need to be applied at specific times to get the best efficacy out of them. And herbicides, some of them, if a plant gets too big from one stage, then if you applied the herbicide, it would damage the crop at that point. And so being able to predict when it's going to hit those certain growth stage is very critical. And the growth and development is driven by temperature as one of the main parameters. Being able to predict that is a real critical factor for those companies, because they want to advise farmers to say, you should apply this fertilizer now or this fungicide at this time. And that will ensure that the farmer applies at the optimum time and then gets the best result and the best experience. And then they will go back and then purchase from that company for them. They also use it for their own seed production as well, to see, okay, what they're forecasting that they're going to produce, so they know how much they're going to have to sell the following year for them. And they're also in countries, those manufacturers sell to distributors or retailers who provide agronomy services to farmers, and they will go out and they will sell the products to them, and they require information to help them with their agronomic services. So when's the best time to go out and check that field? Which fields are maybe struggling, to prioritize which they go out and scout, look around that field to find the problems, and then come up with a recommendation on how to solve them. And they have their own software departments as well, so we provide them with the same type of data, and then they put that into their systems to analyze those different crops within there. And other ones are food companies, someone such as a Nestle of this world, and what they are looking to do is particularly on the sustainability of their crops that they're sourcing. One of the first things they want to do is to identify when they're sourcing particular crops. If we took someone like a PepsiCo with potatoes, they want to know in different regions what the estimated production is going to be, to help them to ensure that they can supply all the supermarkets and other areas with sufficient amount of crisps or potato chips to them. And that's when saying sourcing of supply is a big area, and sustainability. Companies want to be able to monitor how much water has been used for the produce that they're purchasing. And another area is for, I mentioned regenerative agriculture. A lot of those companies are implementing that, and they want to demonstrate the benefits that they're providing to them. And also, they are encouraging biodiversity on farms and want to demonstrate that that's having an impact locally. And so that's another area that it can be used for them. And we also have clients who are Earth observation analytics companies who are using this data and then merging into the products that they supply.
Wow, that's a variety of stakeholders.
So you mentioned a lot of basically applications ranging from financial stability to food produce and farming itself. Are you also looking at other areas? Because you mentioned at the very beginning of our conversation things like urban heat. Are you also looking at in other areas to expand?
Yes, we're open to multiple different use cases that customers may approach us with. Urban heat islands is one that we have been looking at, and we've been supplying data to them to identify which parts of a city are at risk of there being heat events that may be dangerous to the occupants' health, and looking at how different structures and vegetation in areas, how that affects the temperature across a city. And even people looking as urban planning, looking for thermal data to help them manage where they build roads, what the structures are they have in place for those too. And other areas we've had people inquiring about for geothermal identification of areas that could be used for geothermal power as examples too. And even look and yeah, so there's quite a wide range of different applications that we've had people approach us to. Another area was looking at road monitoring, particularly for when looking in during cold periods and where they need to apply salt grit for when it's icy. And other areas including sort of mining, people looking at Turkey using it for assessing potential new sites or what the current output is on existing sites with their reservoirs. And sea surface temperature is another area that people have been looking at too.
A broad range of possibilities.
Yes.
What about science? Are you looking into collaborating with scientists, providing them research data, or validating or things like that?
Yes, we are. So we are looking to work with scientists who are maybe doing PhDs and research particular areas, and also with our clients too. We have a collaborative approach with them where they would approach us with a use case or a study, and we would go on a journey with them, providing the data on that specific area of interest and looking at the time frame that they have. And we work with them to evaluate, is the data applicable for that use case and study that they're doing, and what can we do to improve that data or make it more applicable to that particular use case that they have.
Right. And are you looking for some other partners too?
We're always looking for other partners, particularly in the scientific areas and in research, um, and particularly helping out those ones um, who are looking to solve particular challenges, say, in as talking about like food security in developing countries, as an example.
All right. So, how can potential collaboration partners reach out to you?
They can reach out to us via our website. We have a contact form on there, and they send us in term that from that form they can provide us their details, what they would like to discuss with us, and then contact us there, or they can contact us via info@constellr.com.
Charlie, you've had a very interesting career as an agronomist, working both from terrestrial applications to space applications. So, what kind of skill set or degrees are required to pursue career as an agronomist like you and work with satellite applications?
I would say now probably less and less requirement for specific degrees. I think a passion for biology and also geography within there. Those were two of my favorite subjects going through, and also a passion for helping to feed the world. People can come from other industries. I worked with someone prior to becoming an agronomist. He was a police officer, and he got into it through having worked on some farms in his spare time, spent weekends helping out, and then moved into the industry. And it's just having that real passion for the food industry from there, and being open to how the technology can be used, and bringing people from other industries into it is really a great way for people to, it's really great for the industry. And what I think we really need, well, what someone would really need is to get some experience of actually going to a farm and seeing what happens there, and so understanding what the day-to-day struggles are for a farmer. I do recommend that people watch programs such as Clarkson's Farm, which is a show which really just shows the sides of farming that are the real struggles there. But for an agronomist, in terms of there, so in the UK, I went through a training program called BASIS, which is for agronomists to be certified in the UK, and that takes about a year of study through those, where you're going through walking crops. You have to do a project in a particular area, and then once that application, you've got that qualification in the UK. It varies in different countries what you have. It's just about continuously learning, doing research on which crops to look into, and some of the main ways into it are by going and applying for jobs, and getting experience with the distributors and retailers that I mentioned, or getting some experience of working on a farm within there. And then a lot of the big companies out there who are manufacturers, there may be a route into those, maybe working in a different department, but then requesting for there to get experience, saying that you want to move into agronomy, and then go into those areas. So some of the big ones that I've worked at, there have been people that have come from a non-agronomic background, and then they've moved gradually into the trials and research area, and then managed to gain the experience and knowledge to have an impact and working in agronomy.
Sounds very interesting. It looks like there's a lot of ways, there's a lot of possible inroads into pursuing this kind of a career.
Yeah, but I mean, my main message to everyone is there's not really limitations. If you really want to get into it, then we need more people in the industry, and we need people with different perspectives as well.
Absolutely. This has been a very, very enlightening conversation for me as well, personally. And thank you, Charlie, so much for bringing a lot of end user perspectives to the whole thermal remote sensing discussion. So thank you so much for that.
No problem. Thank you.
Hey, Charlie, thank you so much. The thermal remote sensing community is growing currently very dynamically. So looking into various applications, and the special interest group that we're leading has been asked quite a lot about how to use the data and what are the different applications. So I think the podcast that we have just recorded is going to be a very important asset for that. So thank you so much, and I hope this will also enhance your collaboration opportunities for the future.
Brilliant. Thank you very much. And one thing I suddenly just remembered in terms of you asked about my journey into remote sensing, and 10 years ago I did a product launch at Syngenta, and we did the launch actually at the Space Centre up at Leicester. And
Wow.
so I'm kind of like a circle back and somehow coming to space and with crops, but
All roads lead to space, huh?
yeah.